opening the parentheses tonight to have an excellent discussion. I'm Arthur Smiles. You're watching List NYC. And I don't know about you guys, but I've been so excited about this talk. I just want to get started. So Kai Schmidt, inventor of the Wewa language, is going to talk to us about his quest for Tacit. Thank you, Kai, for coming.
Thanks for having me. All right, let's get started. All right, thanks for coming, everybody. This is my talk, The Quest for Tacit, Combinators, Arrays, and Beyond. Because this is a Lisp group, I should say that I am not actually a Lisp programmer, but hopefully we'll find some...
Yeah, before we start, there's an echo. I'm just trying to figure out where it's coming from. Did you have like...
Did I have what?
Oh, okay. Sorry, that was on me. Okay, I found it. Okay, continue. I'm sorry.
No worries. All right, so this is about my exploration of trying to maximize tacit code. And we can get right in to what that means. So tacit code is code that does not refer to values by name. So any like pipelining of functions, any implicit calls, any way that you, in general, don't have, say, local variables and things like that. Another word for this is point-free. It's a common term you'll hear. But why would you want to do this? And the main idea that I like to think about is the idea of these ceremonies that we do. The ceremonies are the code that you write that doesn't really have much to do with the problem that you're trying to solve. It's just something you have to do. And it can be a lot of things. Boilerplate, we usually think of as kind of a ceremony, but it can be more than that. A lot of the time, a lot of the syntax you have to write, the functions you have to call, lots of stuff. Here's an ancient ceremony that people have been performing for many, many years. But of course, the only thing you actually care about in this program is these highlighted parts here. You care that you're printing something, you care that it's hello world. And really, this grayed out part is part of the ceremony that you do to make this code run. Here's another one in my main language of choice, Rust. And while it's a little shorter, there's still a good chunk of it that it's not important to the problem I'm trying to solve. Really, when I'm trying to find the sum of squares of thing, I don't really care that I'm iterating or that I have to map something. I care that I'm multiplying, and I care that I'm summing, and I care that I'm giving this thing a name. And because this is a Lisp group, I have this one as well. I'm not telling you what the function is yet, but this one in Common Lisp. And really, when you try to pair out like what is really critical, what is the actual meat of this code, it's much less than what you care about. And of course, I'm not a Lisp programmer, so there might be better ways to write this. Another thing to keep in mind that what's implicit in this code is the ordering of variables and your calls and things. And what's really important and not important is, of course, subjective. And if you couldn't tell already, this is, of course, a matrix multiplication function. And so what we care about is that we're doing 3 loops, basically, and that one of those is adding things and one of those is multiplying things. And so we should ask, are ceremonies necessary? Are there ways to avoid them? And is there some design that we can do to avoid them? And should they even be avoided at all? Because after all, who really cares? For one, having to write things like system out println, list.iter.map, lots and lots of parentheses. Depending on who you are, depending on what you're writing, depending on how much of it you have to write, it can be very annoying to have to read, to write. It makes everything longer. Things like this can obscure the meaning because you have to search through your code for the parts that are really important to you. And important for your understanding, if you need to refactor something or just to explain it, to read it. They can get really verbose. And what might be the most or least important thing, depending on who you are. In my opinion, having copious amounts of ceremony in your code is not beautiful. And I think it's important, or it's important to me at least, that my code is beautiful. And so we have Tacit. And to me, Tacit is more about than just having fewer names. That's the common thing you'll hear about it, but really, names are a form of ceremony. Giving things a name, referencing them later. We don't really necessarily care about what the names of things are. We care that we're doing operations on data. And so to me, having Tacit code is really about having less ceremony. And when you have less ceremony, you can have more beauty. So how do we do this? Most languages, in the way that they're designed with their syntax and semantics and things, have ceremonies that are required. Things like defining functions, all kinds of syntax around, say, closures or calls or destructuring, structuring, types, lots of stuff. Some have less than others, obviously. You can alleviate a lot of the ceremony you have to do with just having libraries and things. Lots of languages have macros to alleviate a lot of this, but there's only so much you can do, I think, without redesigning how you approach your solution to problems. And so when trying to write Tacit code, there's lots of strategies that you can use, or that a language can use in its design. And none of these are anything that I personally came up with. I've pulled these all from lots of different sources. A really common one is Combinators. These are functions that express some kind of common function application pattern. Haskell uses a lot of them, but they're common in many languages. Think of things like composition, partial application, anything that would call one function on multiple operands, or multiple functions with just one operand. Things like that are ways of combining functions and arguments in very common ways that you can use to abstract things. There's lots of languages that are based on a stack, where instead of passing things to values by name or inside, you push and pop values from a global stack. Of course, some assembly languages work that way, but also higher level languages, the original being Forth. There's also languages like Factor and Joy that do this. You then have the array languages, some like APL, J, and BQN, where you have most operations working on multi-dimensional arrays. And one of the greatest strengths of this in terms of achieving Tacit code is that you have to write much less. You don't have to do looping and mapping and things, because many operations apply to an entire array. So instead of, say, looping over and adding 1 to each element of an array, you can just add 1 and it just works. Another thing you can do that some languages have is built into the language itself. You can have lots of built-in algorithms that try to solve the thing that you would normally do, whether this is a syntax or standard library functions or special operators and things. And then perhaps the most controversial way of trying to make your code have less ceremony is to use glyphs instead of names. And so I've kind of taken all of these, and I have made a language called Wewa. And Wewa is my exploration of trying to make it so that we can write this low ceremony code but still in a language that is workable and usable for real applications. And so Wewa is a stack-based, array-oriented language with rich support for combinators. And just because I can and for fun, those 3 examples I showed earlier of code that had lots of ceremony, I can put all here. And so now we can get to, you see something like this. And people see something like this, and they have a lot of different reactions. This is just paraphrase of a few of the reactions I've gotten when people see something like this. This is one of the most beautiful things I've ever seen. that makes me feel good when I see that. Other things like, this is cool, but it's not really readable. And probably one of my favorite responses I've seen, what is this garbage? I'm not convinced anyone likes languages like this. And that's an okay reaction to have. But I hope that I can convince you that just because you have symbols for things, this can actually help readability rather than hinder it. And that by encapsulating common algorithms into very short pieces of code, this can be a very powerful concept. And so Wewa is all in on Tacit. And one of the biggest ways in which that's the case is that there are no local variable bindings. You cannot name a local variable. You can have global names for things, you can name functions, but within a function, you cannot give something a name. And one of the guiding principles of Wewa's design is to try to minimize the ceremony we do, with the caveat, because you can minimize ceremony to a huge degree, but it's also important for Wewa that code remains readable. There's lots of things you can do, especially taking from stack-oriented languages, where you shuffle the stack a lot and move things around. And you can write it all out, and then you realize when you go to try to change something that you have no idea where the stack is at any given point, and your code becomes unreadable. So all these things kind of push and pull on each other, and the design of Wewa is about finding a balance between trying to be tacit, minimize our ceremony, but also have a language that is usable. And so that's the end of the slideshow. I'd like to go into a live demo. Do we have any questions before I get into that?
I'll start. Okay. Oh wait, actually we do have whoever raised their hand. You can start first.
I just wanted to see if it's possible to see this. I saw the Tacit program that you were presenting, but I didn't see the code that it actually represented originally.
Yeah. So we've got our hello world, our sum of squares, and our matrix multiplication.
Okay.
And so if I go back here, we can see our.
I saw the matrix multiplying list.
Yeah,
so,
this one.
Yeah. So this one, I understood this, and the Tacit example basically it's the actual algorithm itself that represents the matrix multiplication, not necessarily. So this is one thing about Tacit programming languages that I don't know if you're going to cover later, but one question that always confuses me is how is one to know from looking at, say, an operator or, say, a Tacit program, what the inputs are and what its outputs are? Is there some sort of assumption that's made when writing a Tacit program?
There's a few ways. In general, you can either do it by, if you give, obviously you have names of functions and things. One thing I like to do, if maybe the arguments to the function aren't clear, is to put a little comment for it that documents that. But often what ends up happening is you don't write quite as many functions, because often, and you can see that's the case here, the body of the function itself is actually shorter than the name. And when you come to be able to read these symbols, you kind of start reading sections of these as the functions that they represent. But we'll see, hopefully, in a bit how you can come to think about kind of your local scope of variables and how the variables live in your code.
So it's not so much variables that, although that is a very important thing to have, it's more of looking at, say, matrix multiply right now. I could see those operators, but unless I knew the operator's inputs versus outputs, it's not clear to me from the program that it is a matrix multiply. Is kind of what I'm getting at. But I think we'll touch base on that later on in the talk.
Well, yeah, actually, when you see the demo, it's going to be. This is a when you actually see the language in action, especially the editor that he has on his website. It makes this a lot easier to approach, because I would say my version of when I look at this is like hey, I want to learn about this new language, and then you see these symbols, and you feel like you're like looking at a cliff. Say,
Yeah,
climb
exactly.
this. It's like I'm a beginning climber, right? Maybe I'll do a hike, and then you see this cliff. But I think I'm already ahead of it a little bit, but I think what you've done has made this type of programming a lot more approachable. So I'm gonna leave it at that.
Great.
Because I have a lot more comments about it. Because I've been thinking about this stuff for a while since I actually first discovered your language. But anyways, if anyone else has a question.
All right then.
Okay,
I just realized I don't have my camera on, so let's do that. Hello.
Oh, yep, I forgot to.
And let's go into the demo. So you can follow. Well, I don't know if you can follow.
I realized I was muted. Can you hear me now?
Yeah, go ahead. Hey, John.
Yeah. In the stack language, there really is no question of how many inputs or outputs there are because there's only one input and that's a stack, and there's only one output and that's a stack.
That is true. However, I do find it useful to think of functions as having a fixed number of inputs and outputs, especially when you're trying to.
Mm-hmm.
Sorry, go ahead.
Do you have a notation like APL stack comments?
Yes, I do.
Okay.
So if you want to check this out for yourself, you can go to Wewa.org. And so this is the landing page, but we're just going to skip all this for now. And I'm just going to click on this little pad link. And this will give you.
And lastly, is that a Lojban word?
Sorry?
Is that a Lojban word, Uiua?
No, Wewa is a made-up word that I made up.
No, just one question. One question, because with a stack language, of course, I could have something that, depending on how the program executes, takes a different number of entries of the stack. So when you say, I was wondering when you say rotation, is that allowed in your language?
In the global scope, yes, that is allowed. Within a function must have a well-defined signature for all inputs. And if, in general, that signature can be inferred in most cases, and at compile time, it'll stop you it'll fail to compile if you declare a signature that doesn't match the signature of the function. But often you don't have to declare one.
Yeah, so it's not intentional that it means happy discovery.
Yes.
Well, it does.
Any other questions before I start showing you how this works?
Let's see. I just want to make sure the screen can be seen. Because I'm seeing your screen on.
Well, I don't see. Where should I look?
Yeah, it's it's down for some reason. Let's see. How come it's not showing up? It says that you're sharing your screen. Could you try unsharing your screen and then resharing it?
Sure.
I can see the screen.
Yeah, I just want to make sure the live stream can see it. Now I can see you. Let's see if the live stream sees it. Sorry, there's just a little delay here. Okay, let's go on. I'll double check that while it's going. Okay, there we go. I see your screen. Great. Okay.
All right, so this is an online editor and interpreter that you can use on the Wewa website. And so we can just type some code in here.
Oh, it just disappeared. Okay, reappeared, so not sure what happened.
All right, so we can see here that I have put 3 numbers on the stack. And I actually have this normally on this website. the top of the stack is shown at the bottom of the screen, and that's so that you can write stuff like this, and the things appear in the order that they appear on the lines. But for the purposes of this demo, I'm going to display the top of the stack at the top of the screen, just for clarity. And so if I write 1, 2, 3, we can see that Wewa is actually executed from right to left. And so what this code does is it pushes 3 to the stack, then pushes 2, and then pushes 1. There's a few reasons for this. Part of it has to do with the heritage of array languages, which also mostly run right to left. And it also has to do with how I like to think about the notation. But if we just do a few experiments here, we can see that. So we've got 1, 2, 3 on there. If reading right to left, I then put a plus. This is going to add the top 2 values. If I put some other numbers, it can multiply. And one of the things about Wewa is you might be thinking, well, how do I type? How do I type all these weird symbols up here? And the answer is that for a lot of these, rather than some glyph languages where you have usually some kind of special key combination, some escape key, and then a key you type to enter a glyph. Instead, what you do is you type the name of something. So if I type the word range, you can see that I got highlighted green, and then I can type 10, and I get an array with the numbers up to 10 exclusive. And because this is an array language and operations will apply to entire arrays, if I go to my 10 and I say times 5, that immediately applies to every item in the array. I didn't have to explicitly iterate or do a map or anything. It just works on the array itself. And so if I do something like 1, 2, 3, and 4, 5, 6, you can add those together. You can add just a 5 to that. This is kind of the feel of how these pervasive operations work on arrays.
So when you're adding the arrays, I take it they have to be the same size, or?
They do. So if I were to do 1, 2 plus 4, 5, 6, that is an error. And there's ways that you can say, you know what, let me add I know these are different, but let me add them anyway. I'm not going to get into that quite yet. But by default, yes, it's mostly a way to catch mistakes in your code, making sure that the shapes of your arrays are correct. Because arrays in Wewa and most other array programming languages can be multidimensional, and not in that they're nested in that you have arrays of arrays, but the array itself can have multiple dimensions. So if I were to say, I'm just going to do another notation here. Another way you can write arrays in Wewa is just by putting underscores between the items. And that just gives me my arrays as you might expect. But if I nest this inside, we'll see that I get a 2-dimensional array. And if I ask, what is the shape of this array? So there's a function called shape. It's this triangle one. And again, all I have to do is type the name of it, and then I run my code, and it activates the formatter, which turns it into that triangle. And so we see that the shape of this array is 2 by 3. So we have 2 rows, each of which has 3 columns. And just like the other array, you could do something like times 10, and it works on every element. So this is kind of the core of working with arrays. And one of the advantages of this is that when you have data in arrays and contiguous memory like this, you can do lots of operations like this very quickly. It's people say it's sympathetic to the machine because of how it's stored in memory. And so
I have one question.
Yeah.
When you have like, I think in your earlier example, you had like +1 and then 2, right? Like, in other words, yeah, exactly. When you write it like that. Now, I've noticed when I was playing with it that if you do plus space 1, it's identical to +1. Is it identical as far as, and that's more of a way of a stylistic decision, or does it actually change what's going on underneath?
No, these are both syntactically and semantically identical. For the most, there's a few exceptions. Like, I don't know, you can't just take out this space, right? That's a 23. But for the most part, yes, the language is not new line agnostic, but it's otherwise white space agnostic.
I also have a similar question. In this case here, when you're doing array addition, like, are you creating a new array, and are you popping the entire collection in to do the element by element addition, or is there some implementation detail behind the scenes that making sure that you're doing in place addition to whatever value?
Yes, there are optimizations in the interpreter that try to minimize the number of times that you actually have to copy the array data.
Okay.
So even if you were to do something, so I'll get into, I guess that's a good segue into getting to how the stack works. So this is my thing on the stack. A very common thing you need to do in a stack language is duplicate, make a copy of your so whatever's on top of the stack so that you have two of them. And in Wewa, that's very simple. It's just the period. And now I have two of them. And to your question, I haven't copied all three elements of this array in the implementation. This is just a pointer copy. And so then if you wanted to say square all these numbers, a perfectly good implementation of that would be to multiply by the duplicate. And we get the squares. And of course, you could also just do the power and power 2. So these stack operations, though, are very common. So for example, we saw the duplicate. I can make lots of these. And one cool thing is that these brackets are not just a notation thing. The code inside them is actually running. So if I were to surround this in brackets, square brackets, I can actually make a multi-dimensional array with all these things as rows. And so it's actually running it's putting this 2, 3, 4, well, it's putting 4 on the stack, then 3, then 2, making that an array, then duplicating that 3 times and putting all that in an array. And so you can do cool stuff like, I don't know, +1, 2 times 3, 4, 5. Sure.
Now I'm confused because you said duplicate time, but I only see 4 entries, not 8.
So it's a duplicate. If we go back out here, we can see each one. So here's one, and duplicate that, and then duplicate that one, and then duplicate that one. So each one of these makes just one additional copy. And then we could put those all together. And maybe I want one of them to be doubled or something. Or 2.
Oh, right. It's only duplicating the top 2 items on the stack at any time.
Oh, yeah, the top.
Only the top.
Only the top element, yes.
Right.
So another very common operation you need to do is I have 5 on top of the stack right now. So 5 is on the top and followed by 2, 3, 4. And maybe I need, for whatever reason, I need 2, 3, 4 to be on the top instead. And so we can do what's called flip. And in Wewa, that is just a colon. And now we have 2, 3, 4 on the stack. And of course, this matters. If I wanted to do subtraction, we see that some people say that this is flipped. Some people say it's not, but let's go do -1 instead. What you'd normally call the right argument is the first one here. So here we're subtracting 1 from 2, 3, and 4. And that's so that you can think of this fragment of -1 as this single entity. But it matters because what if we want to do 1 minus all these things? Well, you can just do a flip here. And now we're doing 1 minus those things. And the last really important stack operation that I want to show is over. And so this is when you take the second thing on the stack and make a copy of it to the top. And so that's a comma. And so 5 was on top, but I made a copy of 2, 3, 4 and put it on top. And so there's lots of cases when you need to do this. In general, all of Wewa's functions consume their arguments. So if you want to keep copies of them, you have to make the copies. And this is done because it's preferable to have to make the copies and then use them rather than it implicitly make copies and you have to get rid of them later. And the way we get rid of them is through the pop function, which is just a semicolon. So if I pop 3 times, everything's gone.
So basically have linear logic.
Yes, you might call it linear. And so if you're not familiar with using array languages, this is a very powerful concept. So for example, if I make my array of a bunch of random numbers, I might say, in a functional language, you would pass this to some kind of filtering operation, right? You'd pass it a lambda or some anonymous function that filters out whatever you want. So but in an array language, that's not usually what you do. Because operations apply to all the elements, if I wanted to say, give me only the odd numbers, well, the normal way you find evens and odds is, of course, by using mod. And so I'm going to say mod2, and this applies to all of the items. And so now I'm left with an array of zeros and ones. Of course, Booleans in an array language, much like C, are just numbers. And so here I have my array. You might call them Booleans, you might call them numbers, but this is showing me where all the, in this case, where the evens are. But actually, no, the odds, sorry. And so because of that, I can then say, this becomes a mask, and I want to keep all the numbers where there are ones. Unfortunately, my original array is gone, and all I'm left with is this mask. But to keep a copy of it, before I do my mod, I can do a duplicate. So now I have my mask, and I have my original, and there's a built-in function for keeping all the things in your mask where there is a 1 and getting rid of all the ones that are 0, and it's called keep. And there's all my odds. And if I wanted just the evens, I could say, give me all the ones where it equals 0. Or you could say not. And so rather than iterating and filtering like you might in a more functional language, or using, say, a for loop like you would in a more procedural language, you do these operations on arrays that apply to all the elements. It becomes very powerful. Another idea of this is that you apply these, some array languages call them operators or adverbs. Wewa calls them modifiers. And so one nice modifier is reduce. So what this does conceptually is to apply whatever function I give it between the arguments of all these. And so if I were to say reduce plus, that sums up all the numbers. Then, of course, reduce times is a product. And maybe I want to find the maximum of all the numbers. This is a pattern that obviously occurs all the time, right? A similar thing to reduce is, say, scan, which is in Wewa just a backslash. And so this keeps a running application of all these. So we get the running max, or the running product, or the running sum. Maybe you want to get all combinations of some numbers. So if I have another array here, I can use a function called table. And maybe I want the times table of these two arrays. And so now we have a multi-dimensional array with all the numbers multiplied. And so all the algorithms that would usually involve some kind of mapping and filtering and these functional type operations just become operations on arrays. And it becomes very powerful because you encapsulate these very common algorithms into, in this case, single characters. And most computation that you need to do can be captured by some sequence of these characters. And so what I'd like to do is build up a more complicated sort of solution. But before I do that, are there any other questions?
I wanted to circle back with just what Ram's question before. I don't know if you noticed this, but when when Kai's programming, right, he just has to write the name of the functions, and then automatically the symbols come up. So this is,
well, that's what I was
worried
going to
about,
ask,
like, oh my
because
God, I need a 1,000-word keyboard. You don't need to worry about this. If you know the name of the thing, then the symbol will come up. And then also, if you check out Wewa.org site, you actually have a reverse mapping. So like in the example programs, if you highlight over, yeah, you can see here he does it.
Yeah, so
right?
if you don't
Where
know
it
what something
gives you
is.
the pop-up, so if you can't read, if you're looking at a thing and you can't quite read it, you can literally just put your mouse on top of any character and see what it's doing. Really a really great way to make this type of programming approachable, because I think there's been a lot of great ideas in APL. To me, it's like the closest thing to really like really using applying combinators for real versus like, oh, here I studied combinators in school and then I just forgot all about them, right? And so, but the hard thing is dealing with this. The syntax can be jarring, not unlike people's complaints about lists, too many parentheses, right? This can also be a little, but this allows, I think, one of the things I like about this language is it feels very beginner friendly for this type of programming. Anyways, so I just wanted to bring that to your attention about Rom's question in particular when he was asking, how do we learn this? There's two ways to learn it. Is type, if you know the name of the function, you can run it, and you can also highlight the character and it'll tell you what it does.
Yeah. I should also note, though, that here on the website, there's a language tour, which is kind of a brief introduction to a lot of these concepts. And there's a much more in-depth full tutorial that guides you through one piece at a time, all these concepts, math, modifiers, functions, control flow, all those kinds of things.
When you define a function, can you define
I don't know if someone's asking a question, but it was very low.
Yeah, I'm saying, if you define a function, can you give it a symbolic name?
Do you mean just give it a name, or you mean give it like a glyph sort of name?
A glyph sort of name.
You can. Currently, for any glyph that's not used by the language, you can. So if I did, I don't actually have a great way of typing them, but yes, you can.
Yeah.
And the way that you might define a function, just to show it, if the thing, and this formats also, and so if you type in a name and then an equal sign, the equal sign will turn into an arrow. And if whatever is on the right side here can't run because there aren't enough things on the stack, like there aren't enough things on the stack to say +1. Well, +1 to what, right? And it sees this and it says, oh, well, then this is a function. And so if I then say F5, we get 6. And this is the main way of defining functions. Somebody asked,
Could I ask a question? A quick question. So yeah, this is very interesting, and it's a combination of things I've seen before over the last couple of decades, which actually is quite exciting, because I thought it's not going to be a new thing that is better than what I've seen before. It reminds me a lot of the HP28C, and I see somebody comment here, the RPN calculator. The HP28C from the 90s introduced a Forth-like language. It's all RPN anyway. But basically the stack can contain anything, right? So like matrices, lists, and also functions. So one thing that they also did nicely is you can take a program fragment, and the program fragment is going to be part of the stack. So you push it on the stack. It's like a lambda, essentially, right?
Yeah, this is something
Is that something you can do as well here?
No, so initially, yes, functions were initially first-class values.
Yeah.
Unfortunately, I've discovered in making a programming language that if you have features in the language, people will use them, and they don't always use them in ways that you would like. Yeah. And one of the main ways that people used first-class functions, especially when they're on the stack and can be moved around on the stack, is it makes code very difficult to read, in my opinion, because you're not just keeping track of where your values are, you're also keeping track of where functions are. Another reason is that it also hurt. It's not trivial to infer the signature of a function. So in Uiua, we can give signatures. And so if this is a named function, if I just type a bar and then say this, I'm saying this is a function that takes one argument and returns one argument. And if this indicates that same thing. If I put a dot here and says I'm adding 1 and then I'm duplicating the result, we would need to change this to a 2. And we can see, so it formats that away, but then it says, oh, there's a function signature mismatch because I've declared that this takes one argument and returns one thing. But because it can see my function here and it says, no, that takes in one argument and gives you back 2.
Yeah.
And so while this is a stack-based language, it's very important, or it's important to the design of the language that functions have well-defined stack properties.
That's great. I have one more follow-up question on that. So in the example you showed earlier about matrix multiply, the sum of squares function was defined right above it in the name. So basically, you can rewrite your program to just use a named function. So the matrix multiply is just a dot, like an inner product operation. So it's essentially the same thing that you used in the definition of the matrix multiply itself. That makes the program self-documenting. Instead of writing a long sequence of symbols, you're just going to expand. Well, you're just going to use a name function in place.
It's all here, and doing something like calling this inner product would not necessarily be clear in this case. And one thing that can happen when you have mixed glyphs and names is that you're searching through all the names for the glyphs. So yeah.
I have one question, if that's okay.
Sure.
So I noticed you said functions are not first class, or if I understood that correctly earlier.
Yes.
Is there at least some way of doing outside of interacting with the stack, a way of doing partial function application? So like create a function by applying a subset of the arguments to another function?
Kind of. So like I said, so I don't know if you would consider something like this, right? Partial application. One thing you can do is make functions that take functions. They take the other functions, but they just don't take them on the stack, right? And so I could make a function, and one thing you have to do with those, they're called custom modifiers, and all you have to do is say, end your name with an exclamation point, or as many exclamation points as functions you want to take. And I could do something like this. And so I've created a function that reduces over something. So if I say I want f plus, and then I want 1, 2, 3. Oh, is that my exclamation point? There we go, 6. And we can do the same thing with something else, which is also 6, so maybe max. And so, yes, you can pass functions in this way. You might call something like this a partial application. I'm not sure.
Yeah, it's basically, I'm essentially asking if currying is even possible some way, but it doesn't. It sounds like there is, but it's not the way I kind of I thought it would work.
Yeah, not necessarily. But one thing is about concatenative languages in general, stack-based languages, is that function composition is implicit, right? So if I do neg plus 1, 2, this gives -3, but I didn't have to do anything to say, hey, do the negation after the addition. It just happens because it goes right to
the
left.
Precedence is not necessarily required there, right? So
yes, there is no precedence in Wewa.
Right. And I get that. It's just, like, let's say simple cases, like let's say you wanted to double earlier every element of a array that's on the top of the stack.
Yep.
You could write just, star 2, or you could have also, I think someone mentioned earlier, made an alias to star 2 to some new operator, in which case, yeah, exactly.
Yeah.
So you could do that now, and now you have that label that you could then use in multiple places, rather than constantly typing in the same operator, set of operators, depending upon it doesn't necessarily say it. It depends on how you name it, and how complicated the number of glyphs are, as to whether or not.
Yeah, you can do that,
right? As to whether or not like you said earlier, the number of characters is more readable versus the other thing once you get used to it. But, it's just something I wanted to kind of see if it's possible in Wewa right now today. All right. Thanks.
Yeah. And so unless there's any other questions.
I wanted to, actually, I saw, I'm watching the comments. A lot of people are bringing up how this is very similar to APL. I'd like for you to describe when you were developing the language, right? What were the problems in APL that you wanted to solve? And and how did the idea of using stacks come together like that?
I'd love to discuss that. So, the main language Wewa was mostly inspired by is actually a language called BQN, which is itself inspired by APL. BQN is an attempt to make a version of APL that is, you might say, more modern, more consistent. It uses a different character set than APL, and what it chooses for primitive functions and how they work is different, but the spirit of it is the same. And one problem that I had, I was introduced to BQN, and I immediately fell in love with the idea of, well, the array paradigm, right? Because it's a very elegant and powerful thing. And it's weird because a lot of people don't know about it. So you fall in love with this concept, and then you go to write the code, and the syntax, APL and BQN have infix syntax. So because APL is based on mathematical notation, right? And what happens when you try to write tacit things like this with that syntax is it gets very complicated very fast. And in order to know what a function does, you have to parse out the whole tree in your head firsthand. The other thing that APL and BQN have that Wewa does not is ambivalence, functional ambivalence. So a glyph in APL or BQN will mean one of two different things depending on whether it's being applied monadically or dyadically. So if you see something like
when you say monadic and dyadic, you mean like
unary or binary? Yes.
Right? Okay.
Yeah. So, for example, if you saw, and this is not going to run correctly, but if you see something like this in APL or BQN, this is 5 times 3, -3, right? But if you see this is, well, monadic X is the sign operator. So this would return 3. And it gets complicated in those languages because you have to parse the expression beforehand in your head so you can determine at any point, is this sign or is this multiply? And it's not just this, it's lots of the characters. And I didn't really like that. The other thing I wanted to make easier was Combinators. So APL and BQN also have rich Combinator support. They have lots of ways of applying functions with other functions on different arguments and things. But that also gets really complicated and I think hard to read. And you're not necessarily, unless you're very seasoned in the language, it can be hard to pick apart an expression. And also, you can only create combinators that are so complex, right? You can't say, make a combinator that takes these 3 functions and these 4 variables and combines them in this way. And when I was exploring the stack, I realized that all the combinators you might be familiar with from APL or BQN, or even things more functional languages like Haskell, all those ones you might be familiar with are trivial on the stack. So like I said, composition is implicit. Just putting 2 functions next to each other, it's not even a special rule. It's just the fact of how the language works. There's a very common pattern of doing something, passing the same argument to both inputs of a function. And duplicating the top item of the stack is that, right? Maybe flipping the arguments to a function. Well, the flip on the stack is that. But the thing about that is that you can apply this in so many more ways. So if you wanted to say, I don't know, you could do stuff like this. There's lots of ways you can combine these stack operations to create all these combinators and not have to, in a way that I think is more readable, and which is also more powerful.
I have another question. So basically the language writes itself from the right to the left, right? It's like taking things from the right and then moving to the left. Like the reverse order of 4th, which is understandable. So if you type, you often see yourself moving the cursor to the left.
Yes,
So
you do see
why not
that.
just keep the cursor more to the left and have the code right, out to your right, sort of thing.
Sorry,
It may be confusing. I mean, but once you get used to it, might work, I suppose.
I knew from early on that I wanted the functions to be the left of their arguments. mainly because that's how I think about functions, whether it's a language like C or whether it's a language like a Lisp, right? That feels better than me. And there's also things like this. And if the language followed the same things, same principles as something like Forth, you would have this, which was really unpleasant to me. And so, yes, one of the concessions I have made that often, yes, you do have to move the cursor to the left. And I often just do that with holding control, so we can go more.
It's essentially going top down or bottom up, right? If we go bottom up, like sometimes we do, because we just have the arguments to operate on, and then we apply another function, and we have to move the cursor to the left. It's really interesting, very exciting stuff. Yeah. I have another question, because I've programmed also a lot of Forth, and written a couple of interpreters myself, and it's kind of like an ugly language, but really fun to work on. Just the language itself is fun, just like this. But one of the things that you sometimes need in Forth is an auxiliary stack. Like the return stack is sometimes used to push things on, temporarily, because you need them a lot later in your evaluation. Now, this is a stack-based language, so you may not have to do that very often. There's no looping things and stuff like that. But what if you have to? You have duplicate, you have over, and things like that. But
yes,
do you also have like a pick operation to pick a value from deeper on the stack and things you can save somewhere temporarily?
Yes. So one of the big design hurdles was overcoming that problem, because it's a very big problem in stack languages. One of the original things I had was what you have in like a Forth or something, where they might call it rotate. Where you you either take the top value and move it to the third position on the stack, or you take the third value on the stack and move it to the top, and you rotate the entire stack. I called these functions roll and unroll, and they did that operation in one direction or the other. And what you find when you move values around the stack like that is it becomes unreadable. It's very hard to read that and keep the state of the stack in your head as you're reading that. And so I removed those, and we have a different solution in Wewa of how you
solve that problem. As far as I can see, that's pretty neat. Yeah.
Yeah. So another thing. So if I wanted to do what I just described, where you'd be adding these three numbers up and multiplying these, right? We have another notation of doing that. And it would look something like this, if I can get it right. There we go. Cool. And now you can see, so I've added 1, 3, and 5, and I've multiplied 2 and 4. And so what you see is kind of this visual selector. These are just modifiers that do certain stack operations. But what happens when you chain them is you get this kind of visual selector of the arguments that you're working with. And so you see I have circles where the positions of the thing in this case that I'm adding up are, and I have circles here of the ones that I'm multiplying.
Okay. Yeah. So you can visualize essentially the access to the stack deeper using your symbolic notation with color coding as well. So you basically why did you pick so many colors? Is there a particular reason? Like you group them together? Can you quickly?
Yeah. So the green ones are monadic functions. So they take one thing, return one thing. The blue are dyadic functions, so they take two arguments. Yellow is monadic modifiers. So modifiers are they're basically higher order functions, right? And the monadic modifiers they take one function in. So something like reduce is a monadic modifier. It only takes one other function. Whereas something like this fork here is a dyadic modifier, and those are all in purple. And so here's its first function, here's its second function. And so there's a good number of monadic and dyadic modifiers. These red ones are constants. These over here are just the stack operations. These are part of another notation that I'm not going to get into right now. But it's just so you can kind of mentally parse it a little easier. Yeah, so it took a long time to come to this notation and these functions. And what's nice about these is that all of these functions, all these modifiers you see here are useful outside of this. You saw earlier, I could just do dip with plus, and that's a useful thing to do on its own. Another one is gap, the other one, which got rid of 1 and then added 2 and 3, which of course you could just pop it first, but there's reasons you might not want to. And yeah, so even when I introduce these kinds of what seem like more niche operations, I try to make sure that they have applications outside of that. So yeah, are there any other questions before I get into a more complex solution?
I assume that the primitives that you have and the buttons that you have above are just that. They're something that's primitive and built in, and as a user of the
Yes.
language, I'm not able to define those myself.
You are not.
Okay.
And so, yeah, you can click these and stuff in the editor, but yes. You can define your own functions, of course, and your own custom modifiers. A lot of these built-in ones are more powerful, and they will, of course, be faster because they're built in and implemented in the whole interpreter is implemented in Rust. So all these built-in things are going to be faster than anything you implement yourself in the language. Okay, so I just wanted to show a not too long example of how you think about writing code like this for a real and get a real result out. So I'm going to build up a not too long solution, and I think which will produce what I think is a very cool result. And so where I'm going to start is if I want to make a function that takes an array like this and upscales it. So I want to turn this array into an array that's something like this. And almost. Okay, so I want to turn this array into this array, and you see that I've turned each of the items in here into this kind of cell of multiple elements. And I want to be able to do that. Maybe I don't just want 2 by 2 cells. Maybe I want 5 by 5 or 10 by 10 or n by n. And so I can start writing this. And so let's say I wanted 4 by 4. And let's do 3. A lot of the times you're thinking about the shapes of your arrays. This is the shape being the list of its dimensions. You're thinking about at what level in that shape am I operating? Am I operating on the top level rows? Am I operating on the elements? Am I operating on the entire array? And so a lot of these modifiers exist to control that access. And so the first thing I want to do in trying to upscale this is I want to make 3 copies of each of these inside the array. And the way I would do that is with each. And so each is your very basic iteration, but critically, no matter the shape of the array, each always applies some function to one single element at a time. And in this case, the function I want to apply is keep again. And so what keep will do is say, look, I've got 3 and I've got 1. And then it'll say I've got 3 and I've got 2. And then it'll say I've got 3 and I've got 3 because of the each. And so it's going to keep 3 copies of each one of these, one after the other. And you can see what that looks like. And so now notice this is still, this original array, if we make a copy of it really quick, has 2 rows and 3 columns. And what we've made is this thing that has 2 of these big cells, each of which has 3 rows, each of which has 4 elements. And if I make this a 4, we can see this is the axis on which that would get longer. And so now I've got this, and so now I have my, in this case, 4 of each number, but in this case, I would need it to be 16. And so what I'm going to do is I'm going to do a transpose. And what this does is takes the shape of the array and rotates it. In the case of a matrix, it's just your normal matrix transpose. In the case of this 3-dimensional array, we can see the original shape of this thing is 2 by 3 by 4. And if I transpose it, we can see that the shape has rotated. Now 2 is at the end here. And when we actually look at the numbers, we see that their layout is different. And now I want to do my keep with 4 again, but we notice that my 4 is gone, right? And if I were to just duplicate it, well, now I'm just keeping 4 on itself, right? Because this is doing this. I'm saying take 4, duplicate it, and keep 4 4s, which is not what I want. And so what I'm going to do instead is I'm going to use that function that we saw earlier, fork, and I'm going to fork with the identity. And so what this is saying is, okay, here's 2 functions. I'm going to apply both of them on the same arguments. In this case, I have the identity here. That's going to discard this bottom thing on the stack and just take this 4. And then it's going to apply this. And because this one takes 2 arguments, it's going to use both of them. So here I have my transpose multiplied array, and I have my identity giving my 4 here. And then I'm just going to do the same thing. So now I have all these numbers in here. They're not quite in the shape that I want them to be in. We see if we look at the shape of this thing, now it's 3 by 4 by 2 by 4. And so I need to collapse some of these dimensions. I want a 2-dimensional thing. This is 4. And so we see that in this pretty output, we're organized in this. We see spaces between increasing dimensions of cells. And just because I've played with this before, I know the way to, I've played with this problem, I know the way to collapse this. So we're going to do a reduce. And instead of doing a plus or something, we're going to do this function called join. And if we want to see how that works, we might say join 1, 2, 3, and 4, 5, 6, just puts them together. And so by reducing with join, you're saying apply join between all the rows of this thing, which basically takes the rows and collapses one dimension of them. And we see that now there's no big spaces between all these elements. There's only these little spaces. And if I were to just collapse those again and do another reduce join, this is not quite what I want. And so before I do that second one, I'm going to transpose again. And now we have my nice upscaled matrix. And if I change this to something else, we see that whatever number I put in here, we get my upscaled matrix. So I'm going to keep that for now. And I'm going to call this up. And now we'll tackle a slightly different thing, but we're going to reuse up later. And if I wanted a big matrix of random 1s and 0s, I'm going to do a little trick. We're going to use a function called bits. Bits takes a number and gives you the big endian representation of it as an array of 1s and 0s. And if I give it a list, I get a matrix of the 1s and 0s that make up those numbers. And so I'm just going to throw some random numbers in here. Let's not do 92. That's probably good. This is my random data I'm going to work with. And what I'd like to do is be able to count what are the neighbors. If for each 3 by 3 grid, how many 1s are in that one? And then for each next 3 by 3 grid, how many 1s are in that one?
Okay, we're back.
All right. So we want to rotate each of these things by these offsets, and so each of these will, because these are pairs of numbers, they'll rotate this array both left and right and up and down. And just to see an example of how rotation works, if we have our number and we want to rotate this by 1, we can do that. We can rotate it by -1, it'll go the other way, and it works for multi-dimensional data as well. So what I really want to do is I want to take all the we have this concept of what we call the array's rank, which is the number of dimensions it has. And so I want to take all the rank 1, because each of these pairs is a 1-dimensional thing. I want to take all the rank 1 items, and I want to use them to rotate what is in this case the rank 2 items. There's only one of them, but I want to apply each of these rank 1 things to this rank 2 matrix. And we have a modifier for that, and it is called level. And so I want to level with the rank 1 objects and the rank 2 object. And what I want to do inside that level is rotate. And what we see we end up with is these 9 rotated arrays. These are all the original rotated by one of those different offsets. And I wanted to add these up so we can do our sum. And that got us half of the way there, so we'll do another sum. And now we have the counts. And if I make a little adjusting here and do a duplicate, you can see here's my original data and here's my new data. So if we were to go and say this cell and count 1, 2, 3, 4 ones, and here's a 4 in the middle of that one. If we go to say this middle one here, we count 2 ones and we have a 2 in the middle there. And maybe I don't want the counts of the centers as well. So if I wanted to say only count the sides of each cell and not the middle, well, I've got the middle right here. I can just subtract it. So what I'm going to do is I'm going to say over. That'll copy my array from the bottom here up to the top, and I can subtract it. And now I have my neighbors without the middles. So we're going to do a few more things on this one. I want to find the locations of all the 3s and the 2s in this thing. And maybe by saying that, you might know where I'm going with this, but let's get there. So if I say, where does this equal 3? Well, that gives us our 2-dimensional mask of where all the 3s are. If we make our duplicate again, we see we've got a 3 here, here, and here, and that's where our 1s are. We can do the same thing with 2. And that shows us where our 2s are. But I need both of them, right? And so one thing you might do when you start out with something like this is you might say, okay, if I want to get where the 3s are and where the 2s are, I can say duplicate, give me where they equal 2. And then here's my original. Here's my where the 2s are. And then I can say, okay, now flip around. Now this is on top. I can do the same thing. What I'm going to do instead, I see this and I say, wow, that looks like a redundancy to me. I'm doing equals 2 times. And so I'm going to use a nice little combinator called both. And what I'm going to do is if we just get this just right, I take this out, we can see that I've pushed 2 to the stack, copied what's on the bottom, or copied the second item rather, and then pushed 3. And so now I have the same array twice. I have my 2 and 3 in between them. And with my both, I'm saying with both of the sets of arguments, call the equals function. And so what's going to end up happening is for this set of arguments and this set of arguments, we're going to do equals both times. And we end up with our 2 masks of 1s and where the 3s are and where the 2s are. And finally, I want to say, okay, I want to find all the places where there's both 2s. Well, sorry, where there's both 2s and there was originally a 1. And then with that, I want to find the places or where there's 3s. If I were to just do a minimum here, we end up with only 0s because it was either 2 or 3s on the top of the stack. And so what I need, we saw it earlier, I need a dip. And so what I did was I said, I want to find the minimum of these 2 things. And so we dip down and do a minimum. And finally, I want the place where either of these has 1s. Wewa has no Boolean operators because they can all be approximated, or not approximated, they're all equivalent to certain other operators. And in the case of OR, that's a max. And some people might be familiar with this algorithm, but we're just going to call this F for now. And we're almost there. I'm going to make a more interesting bit of data here. So I'm going to take the number 5, and we're going to make a, how should we do it? We're going to use a function called reshape. And I'm going to say I want a 10 by 10 list of 5s. Or a matrix of 5s, rather. So here's my 10 by 10 thing of 5s. And actually, I don't want 5s. I actually want 0s. And then I'm going to say for each one of these, add a random number. And so I get my thing that goes off the screen, my list of random numbers. Really, I just want 0s and 1s. So we're going to round. And because it's an even distribution, half of them were below 0.5 and half of them were above 0.5. So we get our roughly equal number of 0s and 1s. Actually, I don't want that many, so I'm going to multiply by 0.6. and now we have a few more ones, a few fewer ones than zeros. And I'm going to call this my input data. If I run this over and over again, we can see that the numbers are different every time. Almost there. We're going to repeat, let's say 100 times. A repeat is another modifier. You give it a function, and you give it a number of times to repeat. And the function that I'm going to repeat that many times is duplicate with f. So 100 times, I'm going to take this thing, duplicate it, and then call f on it. And then it's going to go again, and it's going to duplicate that one and call f, and then duplicate and call f. And it's going to do this a bunch of times. And if I run it, we can see it just does them all and puts them all on the stack. And I don't want them all in the stack. I want them all in one array. And so now I have them all in one array. And finally, I'm going to, for each row in this array, where rows refers to, this is a row, this is a row, I'm going to say upscale that by, let's say 4. All right, and so by having all your operations happen in one direction rather than having them in a tree form, which is the way that most array languages are parsed, you can pick through this one bit at a time to try to understand how it works. And yeah, are there any questions after all that?
Well, that was an awesome payback.
Yeah, I know it took a while to get there, but I thought it was cool.
There's one thing I want to bring up because I've been studying your language. But I don't think you brought it up before, or maybe you have and I missed it. But when you have the parentheses, right? Because we love parentheses here. But the parentheses basically, if I'm correct, it's an inline function, right?
Yes, it's a way
anonymous
of moving things into a
function
function.
that you're going to be using it. That's one function basically that's used by the next argument.
Yes.
Or the modifier.
The way that modifiers work is whatever is directly to the right of them is bound as being inside of them. So in this modifier, the things we bound, because this is a dyadic modifier, we say, okay, here's the first thing, here's the second thing, whatever is immediately to the right of it. In this case, if we were to just say up 4, well, only up would get bound inside it and it wouldn't work. And so we need to put it inside. But there's lots of cool examples like this. So if we go back to the home page, it starts you out with some very basic examples with comments and things. And this is all interactable code that you can mess with. We get to working on strings because in Wewa and most array languages, strings are just arrays of characters. And so here's one that takes all the first letters of these and prints out their first letters in a string. Here's a primes with comments of how it's working. The logo of Wewa is made in Wewa. And so here's the equations and stuff that gives you this logo. And just to prove that it actually works, I'll upscale it to 500 and get a bigger one. Or I don't know, change this number. Now the border's different. I don't know if the sound went through, but this just played a chord of these tones.
Yeah, I don't think it. See if you can play it again. It might not work actually. Yeah, I don't think it's going to work on this, but you can check out the Wewa site, wewa.org.
Yeah. Lots of fun stuff like this. And again, you can go to there's a whole tutorial explaining all about how all this works. So yeah, thanks everybody.
That was good job. I have another question for you.
Sure.
So I see that your functions work on arrays, right? What about the idea of working on streams? Does it work on a stream of data, or have you thought about, like, let's say if you instead of dealing with arrays, dealing with the streams of numbers basically, and then processing through that, how that would work?
I have thought about that, and actually certain I/O operations are implemented as a stream interface because necessarily they have to be. In the repository, there's an example of a very basic multi-threaded HTTP server written in Uiua, and that uses streams because it has to process TCP data. But no, for general data processing, what you might call the array way
Mhm.
is to do the thing on entire arrays. There's nothing conceptually stopping arrays from being lazy.
Mhm.
Well, there's a few things, mainly about consistency. For example, what is the shape of a stream of data?
Yeah.
How do you transpose a stream of data? Things like that. But the other thing is that it would also massively complicate the interpreter, and there you have to be a lot more branches inside of it and cases to check for. So I've thought about it, but it's not something I think I'd like to pursue for this.
Well, you could do something like that using a delay operator, perhaps. Basically, make it explicit, right? So you don't evaluate it, but then you basically have to encapsulate the state as well in an object, and you come back to the fact that you have to have functions as first-class citizens. That makes it even more complicated. It's not just more like a lambda. You need to have a state or an environment associated with that you carry along.
So there are the repeat and the do modifiers. The repeat just does something a bunch of times. The do evaluates a condition on every loop. So you can do explicit loops if you need to, and the way that you keep state in those loops is just leaving values on the stack so that you can use them on the next iteration. So you can have state in this iterative way. So you could manually do a stream-like sort of interface that way if you really needed to, if you needed the performance of that, or if your data was streaming in nature, like coming in from some streaming source.
I just wonder, as you mentioned loops, do you have some recursion construct?
There is no recursion. Originally, I had a recur function, which I worked kind of like I think it works in Clojure, but I took it out. One, because it was impossible to infer the signature of something that had a recur in it, and it also made certain optimizations impossible, and I also thought it was harder to reason about, especially when you're also mixing recursion with stack manipulation and things.
Is there a way to have threading with this, like parallel execution? Is it part of the engine that you've been thinking about?
There is
implicit?
Implicit. A couple operations have implicit multi-threading. One example is if I do a bunch of numbers. There is no sort function, but there is a function called rise. And so this gives you the indices into the array to sort it. And so if you wanted to sort something, you would select those indices. Select those indices, and now it's sorted. The sorting is parallel. Transposing for big enough arrays is parallel. There's a few things that are implicitly parallel. There's also built-in functions to spawn. Where are they? There's built-in spawning for OS level threads. So if you want to do it explicitly, you can as well.
That's cool. Thanks.
Yeah. In the documentation here on the site, there's the big catalog of all the functions. And if you don't know what something does, if I say, oh, what is this? Let's get an example. What is this distribute thing? I can click on it. It shows you some examples with outputs and things. Explains you how it works. You can go to any of these. We can have our nice use cases and things with, of course, with the editor that you can manipulate the code and stuff.
Another question I had, actually, you're actually on the right page, but yeah, you have this whole list of functions and you call them the ocean.
Yes, we have the planet functions and the ocean functions. These are two.
Well, first of all, where did you come up with the idea of calling it the planet? This is like.
Yeah. So
I like the names. It's pretty cool.
Yes, the reason it's called planet notation is so if I click on dip here, it's going to direct me to the tutorial about this. But basically, if I look at find an example of these, you see that what you end up with is what I think kind of look like solar system diagrams, where like here's this planet and this planet and this planet in the order that. Right. So the idea is that mixing these numbers that refer to ranks with these numbers that refer to numbers is weird. And it's also verbose. And often the rank that you want to specify is either infinity or it's -1. And you get this kind of weird thing you have to type out, like this. It is kind of a ceremony you have to do. And so the idea is that instead of doing that, you do something like, in this case, it would be abyss and then D. And so we can see here that this refers to a rank 1 object. So there's one wavy line. This one refers to rank 2. So there's 2 wavy lines. So the concept of what it's representing is still there, but we separated this into its own sort of notation for saying, I want these things to operate at these levels. And the reason it's ocean is because the ocean has depths and levels and things. And so there's these 3 special modifiers. We saw level. There's also combinate and fold. And it's saying these are all things that can work at different levels of different arrays.
Mm-hmm.
And so we have this way of notating that.
Interesting.
Also, it's convenient to have functions that do what these functions do by themselves, which is append numbers.
Mm-hmm.
Yeah.
That's awesome. Just to go more in a general discussion about probably some people might ask why I was interested in having you give this talk, right? It's a little bit of a selfish concept because the way I look at, so we had actually our very first not a live stream talk, but it was online talk, was about April, which is an APL in Common Lisp. So it's treating APL as a domain-specific language. This to me is like something that could easily be used to solve lots of really cool problems simply. But as a domain-specific language, just like we also, like in Lisp, you might have like a prologue that you run. If you want to do some kind of logic programming, you can run the prologue interpreter on your data. I can imagine something similar to that with a Wewa or a Wewa derivative type language, taking some of the, I think your key insight idea was putting stack-based and array-based languages and putting them together. Because I remember actually when I was listening to Code Report, that's when I first got the thing. I was like, I like watching his YouTube channel, but
Great channel.
Yeah, it's a great channel. Anyways, when he said, this is a stack-based language, my jaw dropped. I instantly started super paying attention because I had a really strong feeling. Whoa. Like things started clicking in my head of like the types of problems that I felt APL had. Like I had a similar feeling to what you had on discomfort with APL because of the variable stuff and how things are treated one variable or how functions get reinterpreted and things like that.
Yes.
It seemed overly complicated. My spidey senses weren't, but this I think really kind of nails it and really solves that problem where I've been thinking about combinators for a little while, and it started getting a lot of my gears running to say, hey, bro, stacks, baby, stacks.
Yeah, when you start going down the Combinator rabbit hole, there's a whole Combinator. There's multiple Combinator calculuses, and it gets pretty deep.
Well, on Combinators, one thing there is something. Let's see, an odd business is one fellow Burke worked out what he called the concatenate combinator, which is relevant to this because those are Brent Kirby worked it out, and it's probably for the only person that did this, which is a version of combinator theory with a stack. So all the combinators take their arguments with that. However, to make that work, there, unlike yours, you can't just fix the number of things that will take off the stack because that one has recursion, etc. But then you can't. If you did that, you just wouldn't get a Turing complete thing or anything interesting. In order to have recursion or anything interesting, you have to allow possibility that yes, it could potentially take, an arbitrary number of things of stack as it runs.
Yes. The main things that, when you've got arbitrarily sized data, the philosophy in Wewa is that the stack is not a data structure for you to manipulate.
Yeah.
It's a way for you to pass arguments and it's a combinator space almost.
Sure.
And so when you have variable size data, you're either putting that in an array, or if you really don't know what size it's going to be, you use do, which is essentially a while loop.
Okay, but then you only have the while loop, okay, iterating, as opposed to, more arbitrary recursion, which is what usually you'd have when you were dealing with combinator theory and lambda calculus.
Really, I had never associated recursion and combinator theory in my mind, but that's good to know.
No, I mean, because combinators are just, lambda terms that basically only involve variables. So they're, lambda calculus is about recursion. So it's basically, theory of it's, it is a recursive thing, like when you, for example, show that the S and K combinators can give you all combinators, or you have the Y combinator that does the recurring for you, etc.
I see. Yeah, it's kind of, I mean, when you get into learning about combinators and then you see a stack, you realize, wait a minute, all these combinators that are like this complex thing in some of these other languages are trivial on the stack.
But the combinators, the reference to combinators, I get that, and of course the Lambda calculus. But one of the difficulties with combinators is you always need more combinators. Like SKI is not sufficient. You need a B combinator, you need a C combinator, just for efficiency alone.
Oh, sure.
It makes programs so extremely ugly to write and interpret. And then you have, of course, the combinator implementation where you basically refer to arguments somewhere, but you can view in Wewa as somewhere on the stack instead of like a combinator that takes like the nth argument and operates on. And so there's a strong flavor, I think, of a combinator-like language here, where you can access elements on the stack, like their arguments, provided to passed on to combinators. But the naming scheme and coloring scheme and making more explicit what these things do is really nice. I really like that.
Yeah, thank you.
Yeah. Yep.
All right.
Okay. Do we have any other questions? Let's see. I don't think we have any questions on YouTube or whatever. So we're going to stick around a little longer. However, I'm going to officially close the parentheses on the talk today while we still have the live stream going. I want to thank you very much for this talk. You made this combinator programming a lot more approachable, which is another reason I'm very excited being part of this tonight and you coming over. Because
thanks so much for having me.
Underrepresented thing of programming. Underappreciated. Needs a lot. Haskell's taking all the energy. We need to give some energy to the APL folks, which are doing some interesting, and the BQN guys that are doing some interesting stuff. And you.
I'm sorry for the late interjection. I do have a question.
Go for it. Go ahead.
We've seen a couple data types, mostly characters and numbers. Are there other primitive data types that you support? And
there are four.
And what are the more what's what I'm looking for? What means of data abstraction do you support beyond arrays, if any?
None. There are 4 primitive types, and there is only one composite data type, the array. We've seen all of our numbers here. Of course, strings are also just arrays. So if you can take the shape of this, you can reverse it, and the algorithm is the same. Kind is what are called boxes, and this is a way of nesting arrays. So in Wewa, it's required, and in not all array languages, but some of them, it's required that arrays have a rectangular shape, and that all their elements be the same type. And boxes are your escape hatch for that. So if I wanted my array of 1, 2, and 3, 4, 5, I cannot do that because I can't couple arrays with shapes 2 and 3. This would not be a complete thing. If I add my additional thing, it'll work, but this doesn't. The solution to this is we can use a function called box, which will put these in boxes. And now I have this special notation. And there's actually a special notation because you don't want to have to write these squares on every single one of your things. And so if you just use curly brackets instead, that'll make a box thing. And you can put, it doesn't have to be numbers. I can put strings in here. I can put whatever. And it lets you mix these all up. The price you pay for this is that sometimes, not always, sometimes to work on your box data, you have to unbox it to get your data back out in a way that you can work with it. And the fourth type is the complex number. So
Oh, cool. That's cool.
Now, with your box, when you work on it, can you have the size of the number of things in the box change as you're
Yes.
processing it? Okay.
One thing I didn't even get into, and it's this very powerful concept that's not really in other. There aren't, other than the array languages, I don't really know other languages that deal with this a lot. And it's this concept of this modifier called under. And so if I wanted to, say I wanted to put a 6 onto this one, right? Well, normally you'd index into it and like append a 6 to a list or something like that. And what you would do in a language like Wewa, let's see if I can get it right the first time. You say under and you give it 2 functions. And what it does is it calls the first function, calls the second function, then calls some inverse of the first function to undo it. And so what I'm going to do is I'm going to say under, and I'm going to pick, this is number index 1. So I'm going to pick the thing, if I just do this by itself, just to see it. We pick out our element. And so if I need to append to it, so I need to unbox it first. And then I'm going to, in the second function, let's say join 6. And so what this is going to do is it's going to say, okay, pick 1 out, unbox that, append 6, and then it's going to call the inverse of these in the other order. And so we should see, hopefully, yep. Oh, it put 6 in the front. So let's put 6 at the end. There we go. And it's really, you see this and you're like, oh, that's cool. But what it turns out that it pops up everywhere. This idea of doing one operation under another, where you invert the first operation when you're done with the second. And this is the main way of doing like working on sections of arrays. You can pull out a section with under, work with it, and then under will put it back for you. You can do this to operate in like logarithmic spaces. If you raise to a power, do your math, and then under will automatically log it back for you. There's tons of patterns like this where this is a very powerful concept.
Now, the other thing I was thinking one reason I asked about with the changing the number of elements in a box or whatever is because I could see that, like you said, what I mentioned with combinators, you allow things that change the number of elements in a stack. You don't, but one might then be able to use one of these boxes as a stack,
yes.
and
yes,
then
do
recursion and all that inside the box.
Yes, it wouldn't be very ergonomic. It'd be kind of annoying to do, but yes, you could do that. And I've seen people do that when it's necessary.
But this is a kind of like a meta operator, like a special form, like in Lisp, where you basically have the argument represent an operation that you find the inverse for. So is the semantics then not different than the other operators?
For under or for what's inside of this?
Yeah, for under, because this is not some. I mean, how do you let's say I define my own function, and I'd like to do something similar. So the argument needs to be inspected to figure out what the operator is, but the operator is already evaluated. No, I'm not quite sure if I understand the semantics of this type of construct.
Yes, so
I'm running out of time, so this
that's okay.
is something for offline, but.
I mean,
this is very interesting.
Don't worry, we have unlimited time. I just figured that we were done, but it looks like we want to keep going, so let's keep going.
Yeah. I'm happy to keep going if we'd like to.
We can go as long as we want.
But you can't do anything with it other than use it. You can't do anything with the function stack other than use it to pass functions around.
Okay, that's very interesting. Thank you for your answer.
One other question. We've seen errors pop up a couple times too when you try to do things like mix arrays that don't have the appropriate shapes.
Yeah.
What kind of error handling facilities does Wewa have?
So we have, the main one is this modifier called try. And so what try does is it takes it's a modifier, it takes 2 functions. The first one is what you're trying, and the second one is a catch. So if I did f equals try parse, and I'm just going to do a little pattern here, and can I infer function? Do I need 2 of these? I do. Okay. And so what this is going to do is it's going to try to parse, and parse doesn't have a glyph. It's a built-in function, but I didn't think it was general enough to deserve its own glyph. This will turn a string into a number. And then what I'm going to do is, in the event that it fails, and I'll make this more explicit, this is what that is. I'm going to get rid of the original value, get rid of the error, and just return a 0. So if I do F with the string 1, 2, 3, and if I do F with dog, I get 0.
And so errors or values that are pushed onto the stack?
The error will be a value. So if I were to do, let's say instead of popping the error, I'll print it. And so if I do F dog, it'll print out standard out, cannot parse integer number. And so it's not as pretty as if you had let it just fail. If I just did this, right, you'll get a much nicer error. But yes, the errors can be handled as values.
Would those constitute another primitive value?
Yeah, the value gets pushed to the stack. In this case, it's a string. What you can also do, there's also an assert operator, and it's just a function. And if it's if one of its arguments is not 1, and you usually pass some kind of condition you've evaluated to that, it will throw as an error its other argument. And so you can use that to throw errors. And so your errors don't have to be built-in interpreter errors. They can be just whatever value you want. You could theoretically use that for control flow, but just like any other language, you shouldn't use error handling for that.
By the way, thank you for talking. Good night.
Mm-hmm. Okay, well, not good night yet, because I just want to thank you, Kai, for the talk. I want to thank everyone in the audience here for coming. I thought a ton of excellent questions. And also for everyone on YouTube watching, if you really like the talk, hit that thumbs up button. Also, I don't usually like to bring this up, but next month is Listmas, so we're going to have something very special. And if you don't want to miss it, you're going to want to hit that subscribe button and then the notify button. And if you want to find out what that is, and you want to find out earlier than what we usually show it on YouTube, you can check out our socials at list.nyc/connect. And that's where you can connect to us on Facebook and a whole bunch of other places, and Twitter, et cetera, et cetera. So definitely click on that. Again, Kai, fantastic.